you.
So I would like to introduce Professor Karas from Astronomical Institute in Prague, and now you can talk.
So good afternoon. It's a great pleasure to be in Opava and in RAGtime again. I would like to describe a small calculation or small experiment which we have been doing with Kostas Sapountzis and Agnieszka Janiuk. It is work in progress, so I will be very happy to listen to your comments. In this experiment, we tried to see something which in the end we have not seen, but we saw something else. So I will now describe what we wanted to see and what in the end we end up with. But important thing first, let me also say many congratulations to Professor Zdeněk Stuchlík and wish him long life, good health, but not only to Zdeněk Stuchlík, but also to his child, RAGtime, which is now in very nice age of 22. So it's a great pleasure to be here again. For the motivation, I am showing galaxy Cygnus A, which is radio galaxy with jets, and we saw it already yesterday in, I think it was in Arman Tursunov talk, but for a different reason. This is a multispectral picture where you can see radio jets in red color, and they are emanating radially to the left and to the right, and they are to some degree collimated. This is Fanarov really type 2 galaxy with hotspots at the end of the jets. But I'm showing it especially to remind us that interesting things are happening also in the perpendicular direction. It is seen better in X-rays, which is a blue color here, and there is supposed to be either accretion or ejection, which are somehow interconnected, or people think that they are interconnected with the outflows in jets. So that is somehow motivation to see how these inflows and outflows interact with each other. Obviously, magnetic fields are important. This is well known from spectra of these objects that magnetic fields play a significant role. But we will be now touching the very center of these objects, even smaller region than what is seen here in this inset. You see that the lowest length scale is about 1 parsec, which still takes many gravitational radii, and we go really close to the innermost region now. So what is the initial setup for our numerical experiment? We start with the black hole in the center, the vacuum solution, which I will describe in a second. Then we impose magnetic field. As you know, black holes do not support their own magnetic field, so that must be something which is generated by electric currents flowing outside the black hole, probably in the accretion disk or the torus. And then we put matter or plasma into the system. So after some time, the black hole is not in vacuum because it is accreting. And for the initial setup of this plasma inflow, we use a spherical solution here. We put matter on a outer boundary and let it fall inside. So that is something which was described in 50s by Bondi and is known as the Bondi solution, but then it was followed by a huge number of people, exactly because it is in some sense very fundamental, spherically symmetric analytical solution. But in reality, it can be much more complicated. For example, here I am showing the scheme from Silic and collaborators, where they still maintain the spherical symmetry, but they put more ingredients, also the input of energy from nuclear cluster of stars. And then this Bondi inflow is not only inflow anymore, but there is also the outflowing gas in the outer layers, because the stars in the nuclear cluster are adding more energy at certain radius. But still, close to the black hole, the inflow prevails, obviously, because the gravity of the black hole wins in the end. So we start with this inflow from large distance, and the inflow goes onto Kerr black hole. So that is vacuum solution. We don't change the metric or the gravitational field close to the black hole. So we still assume that this Kerr solution remains all the time, and that is described by this well-known solution of Kerr. And as the third ingredient, apart from plasma and black hole, we add the magnetic field. Again, for the initial configuration, we set up something which is probably the most simple solution, a uniform magnetic field, which is aligned with rotation axis of the black hole. I am showing two examples of magnetic field lines around vacuum black hole. On the left side, it is Schwarzschild solution. The vacuum field really looks like vacuum field. On the right side, it is the maximally rotating Kerr black hole, and the vacuum field doesn't look like uniform near the horizon. You notice that there is some effect of expulsion of magnetic field lines which do not thread the horizon anymore. In the intermediate spins, the magnetic field lines will be slightly bent, but they would still cross the horizon. But in the maximally rotating case, the field lines flow around. And what we would like to see is how this expulsion, this Meissner effect, is affected by the inflowing matter, which is eventually coming from the outer boundary, and it is accreting onto the black hole. Or maybe it will not be accreting because there is this magnetic field which is not ingredient of the initial Bondi solution. So we set up these initial conditions, and then we run using the two-dimensional harm code, which was already used in the previous talk and also in before yesterday. So we will see what will happen. On this slide, I am showing the vector potential for the initial magnetic field, which we saw on the graph on the previous slide. So it is just to demonstrate that we have an analytical form for the initial magnetic field. We have analytical form for the initial Bondi inflow, but then we have to solve their interaction numerically. And as you can see here, as soon as matter from outside starts accreting onto the horizon, the magnetic field lines are dragged into the horizon. You see that they do not resist at all. These field lines are constructed near maximally rotating black hole here, but still they start threading into the horizon very quickly because they are embedded in the plasma, and the plasma is accreting due to strong gravity. The colors correspond to the density. So you can see that initially it is just spherically or more or less uniform, spherically, symmetrically falling inside. But after some time, you notice in the equatorial plane, there is overdensity emerging, and that is forming some kind of equatorial disk-type structure. So these field lines go into the black hole, but something is emerging in the equatorial plane. I will show the same situation, but over a larger scale of radii and over a longer time. So you can see that again the field lines are dragged into the horizon, but in the equatorial plane they start to be too close to each other, which eventually produces these reconnection events. For us, it is only the numerical resistivity which operates in the code. It was also mentioned previously that we do not have any real resistivity, but still you can see that the magnetic field lines somehow reconnect here for numerical viscosity, and they start outflowing because of the magnetic pressure. So after some time, this vertically uniform homogeneous field is more like radial or split monopole near the horizon, and in the equatorial plane it starts reconnecting and driving some kind of blobs or disk type ejection along the equatorial plane. It is 2D simulation, I just remind you. And this 2D is usually it is invoked for simplicity, of course. Of course, it is easier to perform long duration computation in 2Ds. But here it makes good sense because it is well known that this Meissner effect operates only in axially symmetric situations. So we didn't want to harm with the harm the Meissner effect. We wanted to maintain this 2D symmetry, and we used 2D code therefore. But still we see that even in 2Ds, as soon as we add the plasma, Meissner effect disappears. But what appears is the emerging reconnection, because this Meissner effect disappeared and the field lines are bent and they start reconnecting. So we can look to some characteristics of this solution. This is magnetic flux across the horizon of the black hole for 3 different spins, slowly rotating 0.6, 0.95, and then almost maximally rotating 0.99. It starts from very small number initially, and then you see that as the accretion proceeds, the magnetic flux is dragged onto the horizon and it starts growing in absolute magnitude. It goes to negative values in my notation. But after some time, as the matter starts outflowing and also magnetic field lines starts outflowing, at this point around 1 or 200 in geometric units, the magnetic field starts dropping again in all cases of spin. And then we can look to accretion rate. I am showing here 1 over m dot because it's easier to visualize. or distinguish the curves. And as you see, these curves are growing, meaning that m dot is decreasing. Again, depending on spin, there are differences, but uniformly it drops as time passes. And we also see some glitches here or here, if you can see my mouse. So they are not just numerical. These are these moments when the reconnections happen and some blobs create the temporary increase in accretion rate. So decrease in 1/m0. I think it is maybe something similar to what Agnieszka was showing, except that here it is because of the magnetic field reconnections. And I think that is all important that I wanted to show. So just to summarize quickly what we are doing, we started with the uniform field, which is attributed to the Wald solution. And we used the analytical form for that at time 0. We started also with spherically symmetric Bondi solutions and used the analytical solution to have it at the outer boundary, and then evolved the system into these. And then we observed how this accreting plasma develops the outflow in the equatorial plane. So thank you very much. I think I was faster than my time limit, but will be happy to ask questions if you have any.
So thank you very much for a very nice talk to Professor Karas. And now, if there is anybody who would like to ask, are there any hands?
Yes, if I may.
Yes.
Right. So that's very interesting results, Vladimír. I think you showed very convincingly that these outflows, as you call them, are associated with reconnection. So I would like to comment that such equatorial backflows are quite common in disk accretion, and we are going to have a talk, I think, tomorrow by Ruchi Mishra on a similar effect in accretion disks, not necessarily around black holes. Mm-hmm.
Yes, thank you, Wlodek. I know, of course, about these solutions. I think difference here is that we really do not have any accretion disk at the beginning. So
I understand, yes.
Flow out starts just from this magnetic field only.
Mm-hmm. Thank you.
Well, probably it is the similar effect as you see.
Can I comment something? I think in a simulation of puffy disk, we can see a similar beginning of similar outflows. And we have also no disk at the beginning. So, yeah.
Okay, I have also one question. So is the resulting field somehow related to parabolic Blandford-Snack solution?
We start with this Wald solution, which as a boundary limit has purely uniform field, which is not embedded into this accretion disk as Blandford Payne solution. But in the end, it develops into the split monopole configuration. I think this what is seen. Well, maybe I cannot reproduce it quickly, but in the end, magnetic field lines go into the horizon here and out of the horizon on the upper hemisphere, so into the horizon in the lower hemisphere, and then they go out. So this is the split monopole, and then we do not keep this accretion disk here fixed, which would thread the field lines.
Okay, thank you for an answer. Are there any more questions? If not, then thanks, Professor Karas, again.